In this video, we're going to talk about empirical probability. And in empirical, when we use empirical probability, we take the observed frequencies of what happened during an experiment rather than looking at what could happen. So we're looking at what actually happened during an experiment versus what could have happened. So take an example like we roll a die. Normally with theoretical probability, we say, oh, well, there are 6 options, 1, 2, 3, 4, 5, and 6. And so if I ask you, what's the probability of rolling a 2, we would say, well, it's 1 out of 6 because there is 1, 2 in the bunch, and there are 6 total, and so the probability is 1/6. With empirical probability, we're going to use an actual table, of 100 different times a single die was rolled, and we're going to look at, well, how many times was the 2 rolled? And so we look next to the 2, it was rolled 23 times. So the probability of rolling a 2 based on this experimental situation would be 23 out of 100 because 23 times out of 100 total. And if you added these up, you would get 100. It also tells us in the beginning of the problem that it was rolled 100 times. And so let's look at B. What's the probability of rolling a number less than 5? So less than means not including 5. So we're looking at 4, 3, 2, or 1. And so really what we have to do is we just have to add all of these probabilities up. So 20, 23, 14, and 10. So 20 plus 23 plus 14 plus 10, and that's all going to be divided by 100. And if we add those all up, we end up getting 67 over 100. And just like when we did probabilities in previous videos, you could take the fraction and we could find a decimal for that. So that's 0.67. In this case, it's 0.23. Neither one of these can be reduced. So either the fraction or the decimal would be a good choice there. And then C, what's the probability of rolling a 3 or an even number? So let me go ahead and I'll just erase the last one here. So let's look at our chart, and out of 100, so it's always going to be out of 100, we're going to circle the frequencies that represent either rolling a 3 or an even. So we roll a 3 14 times, so we definitely want to count that. A 2 is an even number, so we want to count 23. 4 is an even number, so we want to count the 10. So we're taking just these frequency numbers. So we're adding the 10. And then 6 is an even number, so we want to take that 15. And so we add all of those numbers together. So 14, 23, 10, and 15. And we end up getting 62 out of 100. Now in this case, you can reduce it. So you could divide both of these by 2. They have a common factor to get 51 over 50. Okay, we could use our calculator and do 62 over 100. And then we could hit the simplify button and get 31 out of 50. We could also divided in our calculator, which we really didn't have to do because 62 over 100, we know that we can easily write the decimal for that as 0.62. So 0.62 or 51 over 50 would be the best ways to write those answers. Okay, let's look at D. So what's the probability of rolling a 7? So let me go ahead and just erase what I circled before, and we're going to look at just the amount of times we rolled a 7. Well, we didn't roll a 7. There isn't a 7. So what do we do when there isn't an outcome that matches the question? Well, we say there's a 0% chance, or a 0 out of 100, just a 0 probability of rolling a 7. It can't happen. And then what's the probability of rolling a number greater than 100? Well, not 100, greater than 0. All of the number on the die are greater than 0. So all of these frequencies, 100 out of 100, are greater than 0. And that's the same thing as 1. It's also the same thing as 100% chance. So we could say the probability of rolling a number greater than 0 is 1, or the probability of rolling a number greater than 0 is 100%. Okay, so next we're going to talk about the law of large numbers. So the law of large numbers says that as the number of repetitions of an experiment increases, the empirical probability of an event gets closer to the theoretical probability. So in our last example, we found that the experimental probability of rolling a 2 was 23 out of 100. So that's a 23% chance of rolling a 2 based on that experiment. That was just a one-time roll the die 100 times, let's see what happens. Theoretically, if we have 6 choices on a die, so 1, 2, 3, 4, 5, or 6, there's a 1/6 chance of rolling a 2. And if we find the decimal equivalent for that, if we divide 1 divided by 6, we get 1.16 repeating, which if we round is about 17%. So if you notice, the probabilities are different. There's a little, we rolled a 2 more than you would expect just in that experiment. And we know every time we do an experiment like this, we're going to get different results. What the law of large numbers says that if we were to do this a large number of times, so let's say you rolled a dice maybe 1 million times, you would find that the probability of rolling a 2 based on that experiment would be closer to 17% than it was in this experiment where we only rolled it 100 times. Let's do one more empirical probability example, this one with a table. So the following table gives a breakdown of a town with a population of 78,000 people according to age and tobacco usage. Find the probability of each event below for a randomly selected resident of the town. So we can right now, before even looking at these specific questions, already put 78,000 in the denominator for all of these. So let's go back to the first one. What's the probability that the resident was a smoker? And so the smoker is this entire column. So we can take both of these numbers, so 3,900 plus the 15,600, and add those both together. So 3,900 plus 15,600 gives us 19,500 divided by the 78,000. And we get 0.25 as a decimal, or we could say 1/4 as a fraction, or even 25%. So there's about a 25% chance that the resident is a smoker. Okay, so part B adds on to it a bit. So what's the probability that the resident is a smoker under 30? So now both of these have to be true in order for us to count that number. So we're going to look for smoker and then under 30. Those both meet at 3,900. So it's going to be 3,900 over the 78,000. So I'm just going to put that in my calculator, and I get a pretty small decimal, so there's a much smaller chance of this happening than, or a resident being a smoker under 30 than just a resident being a smoker in general. So we get this decimal 0.05, which is equal to, not about, it is equal to 5%. So there's a 25% chance or a 0.25 chance that the resident's a smoker, and then only a 5% or a 0.05 probability of the resident being a smoker under 30. Okay, C, so what's the probability that the resident is not a smoker under 30? So because we did the complement above, we can just subtract from 1. So the probability of a resident not being a smoker under 30 is just 1 minus the probability of being a smoker under 30. So we could just do 1 minus 0.05 and get 0.95 or 95% and be done. If you wanted to look through the table and find the numbers that apply, we could also do that too. So if we want a non-smoker and then under 30, well, then we'll circle those numbers. So we circle this number, basically any number that's not the 3,900, because that represents the smokers under 30. So all the other numbers represent other things, like a smoker that's at least 30, or a non-smoker under 30, or a non-smoker that's at least 30. So we take all of those other numbers, the 15,600 plus the 15,600 plus the 42,900, and those go over the 78,000. So this is, you can see this is much longer to do it this way. And then divided by 78,000. But we still end up with that same answer of 0.95. So you can see the rule of complements definitely makes things a little bit quicker. And then lastly, what's the probability? And let me go ahead and just erase those. So what's the probability that the resident is a smoker or is under 30? So when you see the word or, that means we have to count both. So let's go first and circle everything that represents a smoker. And actually, I'm going to use a different color so we can differentiate. So all the smokers, that would be the 3,900 and the 15,600. So those would be the numbers representing smokers. And then the number representing under 30 would be the 3,900 and the 15,600. Here's the thing, you don't need to double count these 3,900 people. So we're just going to write all of those three numbers down. So 15,600 plus 3,900 plus 15,600. And we're going to add those all together and divide by 78,000. And we get an answer of 35,100 divided by 78,000. So last step, we divide by 78,000 and we get 0.45. So there is a 0.45 chance or 45% chance that somebody from the town, the resident, is going to be a smoker or is under 30.